name is Zara Muhammad. I'm in grade 6 and currently studying in the International School of Bangalore. The topic of my science project today is how Orsted, Faraday's and Lenz's laws come to the rescue in theme park rides.
Here is the structure of my science experiment. First, I'm going to demonstrate Orsted's, Faraday's and Lenz's law. Then, I'm going to show you a real-life prototype of how these laws are used in theme park rides for contactless braking. Finally, I end the experiment with a conclusion. Orsted's law. In 1820, Hans Orsted, a Danish physicist and chemist, discovered that when an electric current is passed through a coil, it produces a magnetic field. Here is a short demo of Hans Orsted's law.
For this demo, I have used an iron nail, some paper pins, a copper wire, and a battery. Usually, metals like iron are non-magnetic metals. When I touch it to the paper pins, they don't stick to the nail. However, if I surround this with some copper wire and attach it to a battery, it will become magnetic, just like this. If I connect it here, it will become magnetic. This is what Orsted's law is. When electric current is passed through the coil, a magnetic field is generated. Orsted's invention was a significant breakthrough because it provided a link between electricity and magnetism.
Faraday's law. In 1831, Faraday discovered that when a closed conducting coil experiences change in magnetic fields, a voltage is produced, and if the coil is closed, an electric current will flow through it. This invention is referred as Faraday's first law of electromagnetic induction.
For this demo, I have used a copper wire, a magnet, and an ammeter to measure the current. This copper coil has 200 turns. When I bring the magnet in and out of the coil, the voltage is generated. Generated current can be seen in this ammeter, just like this. The magnitude of the current is heavily dependent on what type of material is being used, how many number of turns there are, how fast the magnet is moving, and a number of other factors.
Lenz's law. Lenz's law extends to Faraday's law, which states that when a non-magnetic conducting coil experiences a change in magnetic field, a small current is induced. The induced current, in turn, produces a magnetic field in the direction opposite to the original magnetic field.
For this demo, I will need an aluminium plate, a coin, and a small magnet. I'm keeping this plate at an angle. When I drop the coin, it moves very fast due to the Earth's gravity. They fall with a constant acceleration of 10 meters per second square. However, when I slide the magnet, it doesn't slide quickly. That's because there is a force making it go slow. Basically, what's happening is when a magnet is sliding on the surface, the aluminium plate is experiencing a change in its magnetic field. The change in its magnetic field induces a current in the plate. The current in the plate creates another magnetic field in the opposite direction. Due to the two magnetic fields in an opposite direction, the magnet moves very slowly.
So far, We have seen Orsted's, Faraday's and Lenz's law. Now I'm going to demonstrate how these laws are used in real-life applications. Before the demo, I want to give you some background on friction and braking. We know that when we rub our hands, we feel some heat or warmness in our palms. Similarly, we know that when we are riding a bicycle or a car and apply the brakes, the brake pads come in direct contact with the wheel. The direct contact creates friction and the bicycle or car stops. From our experience, we know that friction causes heat and also wear and tear of some parts. This is where Orsted's, Faraday's and Lenz's law comes to rescue us in designing a frictionless or contactless braking system. This type of braking system is used in all theme park rides and modern/expensive cars like Tesla. Here is a demo of the frictionless brake system.
For this demo, I have used a magnet and an aluminium disc. Imagine this disc is a Ferris wheel. The colourful labels are the passenger seats. The disc is made out of aluminium, which is a non-magnetic material. For example, if I bring a magnet to it, nothing happens. However, if the disc is moving, something is going to happen as explained by Lenz's law. The working principle of frictionless braking system is very simple. When a rotating disc experiences a change in its magnetic field, it induces a current in the rotating disc. The induced current in turn produces a magnetic field, and the direction of this magnetic field is opposite to the original magnetic field. Since these two magnetic fields are acting in an opposite direction, the rotating disc slows down as if brakes have been applied to it. If we don't bring the magnet close to it, the wheel just takes lots of time to stop. By bringing the magnet close to it, it stops quickly without any contact.
In conclusion, Orsted's law lays the foundation by connecting electricity and magnetism. Faraday uses that foundation to devise the electromagnetic induction law. Lenz's law extends Faraday's law by specifying the direction of induced magnetic field.
That's it from my side. I would like to thank IIT Titupathi for giving me the opportunity to share this experiment with my fellow students. I hope you liked it. I look forward to receiving feedback from the participants and judges. Thank you and bye.